So today's class is Computer Organization, Module 4, Lecture 6. Now, last day we learned about the I/O, that means the programmed I/O. I have already told you that there are three ways of communication of I/O with the CPU. One is called the programmed I/O, second one is called the interrupt I/O, and third one is the DMA or direct memory access. Last day we discussed about the programmed I/O. Now, what was the problem of program I/O? The problem of the program I/O is that in the program I/O, you know that CPU has to check the status of the I/O devices, and it will check that whether the I/O device is ready to transfer the data or not. If it is ready, it will go for transferring the data. Otherwise, CPU has to again check the status of the status of the I/O devices, that whether it is ready to transfer the input and output data. Clear? So what was the problem in the programmed I/O? The programmed I/O, the problem is that CPU has to check after some time periods. There is a time period that suppose after 10 seconds or 15 seconds or 20 seconds, CPU has to check continuously that whether I/O is available or not. Okay, so CPU has to check the status. After checking the status, if it is available, then it will do the instruction. It will run the instruction. Either if it is a memory mapped I/O, it will be similar I/O instruction like load and store. But if it is a I/O mapped I/O, it should be in and out instruction. It should execute. Clear? So that was the programmed I/O. Okay. So in the interrupt I/O, to reduce the disadvantages of the programmed I/O, the interrupt I/O is used. Okay, this is another technique for communication with the CPU with the I/O. So what happens in the interrupt I/O? In the interrupt I/O, the load on the CPU is reduced. Why? Because interrupt I/O is a device initiated data transfer. That means when the device is ready to transfer the data, it will send the signal to the CPU and tell that, see, I am ready to transfer the data. Then only CPU will do the different types of operation on the device. Clear? Again I tell you, again I repeat, in the previous case, CPU continuously checking the status of the I/O device, that whether it is ready or not. In this case, CPU don't have to check the I/O device. I/O device itself will send the signal when it is ready, and that is called an interrupt signal. Why it is called interrupt signal? Because suppose the CPU is executing some program. When this interrupt signal comes, CPU will stop executing the current program. It will update its program counter. It will go to the another program, which is called sometimes called the interrupt handler or interrupt service routine. That is generally written for the I/O particular I/O device. We generated the interrupt, and it will do the operation there. That means it will execute the routine. After completion of the routine, it will again go back to the previous instruction it was executing. Okay. Again, I repeat, in the interrupt driven I/O, suppose I/O is executing a set of the instruction. Sometimes I/O is ready. It will send one signal to the CPU that, see, I am ready to transfer the data with you. Okay. Then CPU will stop the execution of the current instruction. It will go to the particular program that is called the interrupt handler or interrupt service routine, that is written for the particular device. It will execute that routine. After the completion of the execution of the routine, it will again go back to the previous instruction it was executing. So this is called the device initiated data transfer. That means when I/O is ready, it will send the interrupt. In the previous case, CPU continuously checking, or after some periodic time, that means after some time, it will checking, after some period, it is checking the status of the I/O device. But it is not the case in the interrupt I/O. Interrupt I/O means when device is ready, it will send the signal to the CPU that I am ready. Clear? So what is the formal definition of the interrupt? So interrupt is an infrequent or exceptional event that causes a CPU to temporarily transfer control. Temporarily transfer control means temporarily stop the current execution of the program. Currently, whatever a program CPU is executing, from its current program to another program called interrupt handler or interrupt service routine. This interrupt handler or interrupt service routine is written for the particular device which has generated the interrupt signal. Okay. So we written here the interrupt service routine services the event in question. That means the device which has generated the interrupt signal. Okay. So this is called the interrupt driven IO. This is different from the programmed IO which we have done in the last day. Clear? Now, when I talk about the interrupt, there are mainly three types of interrupt can be found in a computer. They are called the external interrupts, internal interrupts, or traps, or software interrupts. Okay. When processor wants to communicate or IO device wants to communicate with the interrupt signal it is generated is called the external interrupt. Okay. So it initiate and terminate the IO operation, then in the IO device operation. Clear? This external interrupt, there are two types of external interrupt generally. One is called the non-maskable and another is the maskable. What is the meaning of non-maskable? First, I will tell what is the meaning of maskable. Maskable means a maskable interrupt can be enabled or disabled by the CPU. Okay, that means CPU can enable or disable one interrupt signal. Suppose CPU is executing one set of instruction, one interrupt comes. If it is a maskable interrupt, if CPU wishes, it can disable the interrupt. Okay. Then after some time, it can again enable the interrupt. So that is called a maskable interrupt. Okay. But if CPU has no privilege to masking some interrupt signal, that is called non-maskable interrupt. Suppose in case of the fire alarm or power failure, what happens in the case of the power failure? If there is any failure in the power, CPU used to take the backup of its all the programs or the data. And suppose if fire alarm works, CPU has to again take the backup of its all the data. In this case, CPU cannot mask the interrupt. Why? Because the priority of the interrupt is highest in this case. Okay, otherwise there may be a fatal incident may occur due to the power failure or due to the fire alarm. So these all types of interrupt due to the power failure or due to the fire alarm is called a non-maskable interrupt. Processor or CPU cannot stop or disable the interrupt. Okay, but any other interrupt, suppose CPU is doing some another process, very important process, and one interrupt comes, then CPU can disable this interrupt. That interrupt is called a maskable interrupt. Okay, these all are the external interrupts. Then there is another type of interrupt signal that is called the internal interrupts or traps. These generally occur due to the condition of overflow. You know what is the overflow? If a number is generated which is more than the maximum bit taken by a machine or processed by a machine, that is called the overflow. Or division by zero, you know, if anything we divide by zero, it is the infinity, but in case of the machine, it will be a trap or internal interrupts. Okay, or if you written some instruction whose opcode are illegal, that means that is not written in the ROM given by the manufacturer, again it will generate one internal interrupt or trap. Clear? This is the difference between the external and internal. This is only the internal thing of the machine. Okay, but here the outside thing, that means the IO devices or power failure, this type of interrupt is generated in case of the external interrupt. Another interrupt is the software interrupt. This is actually generated by the operating system. When you read the operating system, you will read more about this. Only remember the thing that this is software interrupt is generated by a system software called the operating system. So these are mainly the three types of interrupt in a system. Clear? Now, see what happened in the interrupt driven IO. What is the process? Suppose this is the CPU. CPU is working. This is the data bus. Using this data bus, IO is connected with the CPU. Clear? Now, when this IO device is ready to transfer the data, it will send one interrupt signal to the CPU. That means it will tell the CPU, see, I am ready to transfer the data. Okay. Now when CPU is ready to service the IO device, it will send the interrupt acknowledgement signal. What is the requirement of interrupt acknowledgement? Using that interrupt acknowledgement signal, CPU will find out which IO device requires the service, because there may be more than one IO device. Okay, you know. So suppose it one IO device or two IO device gives the interrupt request signal. So CPU has to find out which IO device has generated the interrupt signal. So for finding the particular IO device, CPU has to generate the interrupt acknowledgement signal. It will send the interrupt acknowledgement signal to all the IO devices. Now, how CPU find out the particular IO device, that I will discuss later. Okay. So this is the process in the interrupt driven IO. Now what happens here? Suppose this is a main program. You know that main program is written into the RAM. So CPU is executing the program here. This is a sequential program execution. CPU is executing. Now here in this position, at the ith instruction, suppose one interrupt comes from this IO device. Okay, one interrupt comes this IO device. When CPU is executing the instruction I, what will happen? CPU will first complete the total instruction. Okay, that means in the total instruction means there are the 5 stages, you know, instruction fetch, instruction decode, memory read, execution, memory write. Only after the last stage, that means after the completion of the instruction cycle, CPU will stop executing the current program. That means the program written here. Okay, it will save the address. Address means which address it has to save? It has to save the address of the instruction I+1 in a particular special type of register. Sometimes that is called a stack. Clear? It will save the address. Then it will change the program counter to a new address. What will be the value of the program counter? Program counter value means the address of the instruction, next instruction to be executed. In this case, that is the address of the particular program called the interrupt handler or interrupt routine. So here, whatever may be the starting address of the interrupt handler, it will be stored into the program counter. Okay. So control now it will be transferred here in the interrupt handler. This interrupt handler will service the particular this IO device. Okay. This is a program. This is also a program. Okay. This program is written for this particular IO device which generated the interrupt signal. So it will service using that program. After completion of the service, that means after completion of the program interrupt handler or interrupt service routine, the control will again back to the instruction I+1. That means program counter now will again reloaded with the address of the I+1. From where I have already told the address is stored in some stack, this address. So from that stack, it will take the data, program counter will take the data and place there, and the control will be transferred, control of the CPU will be transferred from this interrupt handler to again this program. Again, the current program will run. So this is the function of the interrupt driven IO. What is the advantage? CPU don't have to check every time what is the status of the IO device. When it is checking every time what is the status of the IO device, it have to stop the current program. But this is not the case in case of interrupt driven IO. It will only stop the program when one interrupt, that means device is ready signal is generated from the particular device. Clear? So this is the difference between the previous one, that means the programmed IO and interrupt driven IO. So here I have already told there are 3 types of IO operation. One is called the interrupt driven IO, programmed IO, and direct memory access. That I will discuss next day. Now see, all things IO to memory transfer through processor. Clear? In the programmed IO and interrupt driven IO, in both cases, IO device transfer the data to the memory through processor. Both programmed and interrupt driven IO. But in programmed IO, no interrupt signal is used. For this reason, here it is written no interrupt. But in the interrupt driven IO, interrupt signal is used. In the direct memory access, which I will discuss in the next day, also interrupt is used, But what is the difference between the interrupt-driven I/O and direct memory access? Interrupt-driven I/O actually uses the CPU for transferring the data. But direct memory access, it bypasses the CPU for transferring the data from one I/O device to the memory. So direct I/O to memory transfer. This is the difference between interrupt-driven I/O and direct memory access, though both use the interrupts. So it is written here, use of interrupts. But program I/O, it transfers the data from memory to I/O or I/O to memory through processor, but it does not use any interrupt signal. Okay, so this is the difference between the different type of I/O transmission between the processor and the device. Now, there may be the case that in a system there are more than I/O device. Clear? And more than I/O device can generate the interrupt signal. Clear? Suppose there are 1, 2, 3, 4 up to n I/O device, and more than one I/O device can generate the interrupt signal at the same time. Again, I repeat, more than one I/O device can generate the interrupt signal at the same time. So CPU has to service the particular I/O device. Now the question is, which I/O device CPU will service? Okay, so CPU has to give some priority on the I/O device. The I/O device which has the highest priority will be serviced first. Then comes the next I/O device with the less priority. Yeah. So a mechanism based on the priorities is required to service the I/O devices. Yeah. Now there are two ways to select the I/O device based on the priority in interrupt-driven I/O. There are two ways to select the device based on the priority. So what are the two? First one is called the fold interrupts, and second one is called the daisy chain interrupts. Okay, these both are used for selecting the particular I/O device depending on priorities. First, we will discuss about the fold interrupts. Now see here. This is the architecture of the fold interrupt. See, left hand side, you can see here one processor, and the device is connected with the processor. Clear? And this is the interrupt signal. This signal is actually connected with a OR gate. That means this device will generate the interrupt signal, or this interrupt signal from all the devices is connected with the OR gate. First, in the fold interrupt architecture, this is driven by a software. This is not a hardware approach. This is a software-based approach to find the priority of device. Clear? Now the question is how it works. First, suppose device 1, device 2. These two devices generate the interrupt signal. That means this is called the interrupt signal. So this is the OR gate. So this interrupt signal will be high to the processor. So processor knows that one interrupt signal is generated by one or more than one processor. So it will stop the execution of the current instruction. Now processor have to find out which device has generated the particular interrupt signal. Okay. If it has more than one device, processor has to service the devices based on the priority. So in case of the fold interrupt, what happens after generation of the interrupt signal? One particular service routine will execute. That means one particular program is executed. The program is written for the polling the different devices. Polling means finding the device which has the highest priority or which have to be serviced by the CPU. So after generation of this interrupt signal, it will go to the particular service routine. Clear? So in the service routine, what will happen in the service routine? We will generate these signals: PA0, PA1, PA2, PA3. In the signal, it will generate. Okay. Now, how it will generate? In that service routine, the priority of the device is given. Suppose the priority of the device 2 is more than that of the device 1. These two devices has generated the interrupt signal. So priority of device 2 is more than device 1 from the software program or interrupt service and interrupt service routine or interrupt handler. In the handler, it will be written, okay, in a particular general program, it will be written which has the highest priority. So depending on the priority, it will generate the PS0 signal. What is the PS signal? Here it is written, send 1 to the device to check the status. So as device 2 has the highest priority, first PA1 signal processor will send the PA1 signal to the device 2. That means the signal will be 1 and it will go to the device 2 to check whether this device has generated the interrupt signal or not. If this signal has generated the interrupt signal, this line will be high. That means PB. Here it is written PB becomes high if the device needs the service. If device 2 needs the service, it will make this line high, PB1. Okay. So device, when this PB1 is high, processor will go to the particular service routine written for the device, and it will do the transfer operation between the device 2 and device 1. Suppose device 2 has not generated the interrupt signal. In this case, the next priority, suppose the next priority is device 1. So processor will generate the PA0 to high. So it will check here if the device 1 has generated the signal, it will make PB0 as 1. So processor will know that device 1 require the service. So from that particular general service routine, it will go to the particular address where the interrupt service routine for the device 1 is written. That means the particular address in the memory where the service routine for the device A1 is written. It will execute the program and data will be transferred from the device to the processor. Clear? In this way, this software based hold interrupt actually works. Now, what is the thing here? Here, this is a software-based approach, and this is a non-vectored approach. What is the meaning of non-vectored? Non-vectored means here when device is sending the signal, suppose yes, I have sent the interrupt signal, but it will not send the address of the interrupt handler. That means what is interrupt handler? I have already told. Interrupt handler is the address of the service routine for a device 1. Device 1 will not send the address of the particular program. Okay, the address will be generated from a special type of program, that means the general program which is written in the processor. Okay, so this is called a non-vector type. Here device will not send the address of the interrupt service routine. Processor has to find out what is the address of the interrupt service routine. This is called non-vectored type of interrupt. Clear? So this is called the hold interrupt architecture. So the feature is written here. This is handled by software. I have already told. Here CPU responds to interrupt by executing one general service routine. General service routine is nothing but the program where the priority is determined. Okay. So priorities are determined by the order in which routine posed by each device. Routine means the general service routine. So in the program, the priority is written. Clear? Service starts with the highest priority. I have already told. If the device 2 has the highest priority, first it will go to the device 2, then device 1, then device 3. It will be based on the priority which is written in the service routine. Clear? General service routine. It is slow because processor has to poll or check all the devices in the system. Suppose there are 100 IO devices. Processor, depending on the priority, suppose the priority is 2, then 4, then 7, then 8. Depending on the priority, it has to check or poll each device in the system. Yeah, this is the problem with the hold interrupt, and as it is handled by software, you know, software is slower compared to the hardware device. Okay, so this is the problem. This is a non-vector type interrupt. I have already told, because device does not supply the address of the interrupt service routine. Clear? CPU has to find out what is the address of the interrupt service routine. Now there is an advantage in the hold interrupt. The advantage in the hold interrupt is, as it is governed by a program that is called a general service routine. In the program, user can change the interrupt of the different types of devices. That means this is a flexible thing. Okay, as it is software, it can easily change. Suppose it requires device 10 to be the highest priority, not device 2. Then it will change in the program. The device 10 should be highest priority, then comes the device 1, then device 2. In this way, it can change the priority in the system using the software. Clear? This is so it is a flexible, but as it is driven by the software, its speed is very slow. This is a slow device, a slow technique. Clear? So there is another technique that is mainly driven by the hardware. That is called a daisy chain interrupt architecture. First, you listen carefully the architecture. See here also one processor is shown and devices are connected. But there is a special type of connection for the daisy chain. What is the connection? Here, device 1, D1, has the highest priority from all the devices here compared to all the devices. That means D1 should be highest priority. Next priority is D2. Next priority is D3. It will go up to Dn. That means the device which is nearer to the processor will be a highest priority. Here the devices are connected in such a way such that if the distance with the processor is low, device distance of the processor is low, priority will be high. That means device 1 has a more priority than device 2. Device 2 has a more priority than device 3. Device 3 has a more priority than device 4. In this way, which has the least priority, device N is the least priority, device 1 has the highest priority. Clear? So here, this is a dedicated connection. In the previous case, in the fold interrupt, they are connected, but you can change the priority in the software, whatever may be their connection. But here you cannot change the priority. If you want to change the priority, you have to change the connection. Suppose device 2, you want to make device 2 as the highest priority, device 1 as the lowest priority. So you have to take this device 2 here and you have to take this device 1 here. Okay, because you have to make the distance shorter for the highest priority device. This is the daisy chain. Okay, now how it works. See here, processor 1 connected with the different devices. This is the interrupt line of each of the devices. This one, this one, this one. These are the interrupt lines. So suppose 3 or 4 device generate the interrupt signal. So this is generating the interrupt signal. This is generating the interrupt signal. This is generating the interrupt signal. So this comes with the OR gate. That means this interrupt will be high because device 1 or device 2, as it is connected with the OR gate, one or more device makes it high, it will be high. So processor will know that one interrupt has come. So processor now have to know what is the address of the device which has generated the interrupt signal. Clear? So it will generate one interrupt acknowledgement signal here, INTA. What is the function of interrupt acknowledgement? When this is high, processor will after some time will generate interrupt acknowledgement. This will be high. This will be go to the device 1. Okay, if device 1 requires the service, its input is 1 from the interrupt acknowledgement, it will make the output as 0. Here it is written here, device requires service, input is 1, input is already 1, output will be 0. Output will be 0. In this case, see, input is 1, output is also 1. That means device 1 does not require the service. So it will pass the signal to the device 2, making this output 1. So this is 1 means this 1 has passed here. Clear? So it will go to the device 2. In the device 2, suppose device 2 requires the service. This is the next higher priority. Device 2 requires the service. So it will block the signal by making the output as 0. Here device requires the service. So input 1, output 0. So input is 1, output it will make the 0. As it is making the 0, the signal will not propagate to the next devices. Processor will service this device. So device 2, with that, it will generate the interrupt address vector. That means there is a specific hardware which generates the particular address where the service routine for the device 2 is written. In the fold interrupt, the service routine is not generated from the device. Processor has to find out the service routine. Here, with the identification of the device, processor will know what is the address of the particular interrupt service routine or interrupt handler, because here the address comes with the particular device. So this is called a vectored interrupt structure. Previous one was non-vectored interrupt structure. This is called, as the address vector is generated, this is called vectored interrupt service. Okay, so this is the address. So in this way, now suppose device 2 is working. Okay, that means it is transferring the data. In this case, again, one interrupt signal is generated here. Again, processor will send the signal. Now suppose device 1 requires the service. So it will make this one and this output as a 0. When the output is 0, what will happen? Device 2 has to stop its service. Because device 2 is working now, it has to stop because another higher priority device has come, and that higher priority device requires the service from the processor. Okay, in this way, it will break the service of the device 2 and device 1 will go. In this way, the priority is designed. Clear? One thing you must remember, that this is a hardware driven approach. If you want to priority, you have to break the total thing. This is not flexible, but speed is the highest. Clear? In case of the daisy chain interrupt structure, this is called daisy chain. Depending on the distance you are setting the priority, this technique is called the daisy chain interrupt system. So here it is written here, it is faster approach than software polling. The devices are arranged according to the priorities that I have already told you. Raise the distance, higher the priority. Now if one device fails, the system may give fatal error. That is the problem. Why? See here suppose this device fails, the connection is lost. So this signal cannot propagate to the other devices. So system, there may be a fatal error in the system. This is the problem with this daisy chain architecture. But that was not the problem in the old architecture, old interrupt, because in that case, different lines were connected with each of the devices for polling. Clear? So if one device fails, the system may give fatal error. Another, rearranging the priorities is difficult because we have to break the total circuit. It is a dedicated hardware circuit. This is not a software driven circuit. And this is a vector type interrupt, that is a device must supply to the CPU the starting address of service routine, that I have already told. Previous one was the non-vector and this is the vector. So what is the gist? Gist is the, in the interrupt service driven IO, processor will service the IO when it gets the interrupt. Processor don't have to check the IO device continuously, and it is a very good approach because the time is very low compared to the programmed IO. And there is a, if priority comes, there is a two types of technique to handle the priority of different device. One is the software technique, that is called a fold IO, and another is the hardware based approach, that is called the daisy chain interrupt service. Okay, and this is a vector type approach, daisy chain, and fold approach is a non-vector type approach. So this is all for today.